Hi, I'm Jean-Luc Auger with Orange France. In this video, we will see some of the more advanced auto-design feature of GNPy and how it can be used to emulate specific engineering or just optimize the network performance. So we are going to look at the power per span optimization and amplifier output VOA. And we are going to compare the result with a CSV and an Excel graph. So we start with the same point-to-point link that was previously introduced in other videos. So it's an 11-span network with two ROADMs at the beginning and the end, various span lengths, so we can look at the power difference impact of versus span lengths, and still no equipments are defined. It's just a raw dark fiber topology. And GNPy, the tool, is going to perform the auto design by picking the right amplifiers and equipment from the equipment configuration JSON library. So this is a highly customizable multi-vendor library of equipment and engineering parameter, which is what we are going to look at now. So because a multi-vendor environment is not about it's not just about having multi-vendor equipment and an open library with open model. It's also about open engineering and parameterizable parameters for this engineering, unlike proprietary equipment planification tools that hide the engineering parameters and choice that are being made. Here, everything must be configurable to reflect different engineering practices and also to see the advantage of and optimize what we want to deploy in our network. So let's start with the power per span. In the previous simulations, we had performed a power sweep to compare two amplifier strategy across the network, and by this power sweep is basically changing the power per span in all the span, but launching the same power in every span. So all the span here that are modeled have the same launch power, and we vary this launch power and try to find the optimum with that you can see on this curve. For example, we find that 0.5 dBm or about 0 dBm is the optimum launch power when we launch the same power in every span. But the GN model is telling us, if we put some very simple equations here, that the optimum power setting is span loss dependent. So it may not be the optimum to launch the same power in every span. So we could still do the power sweep to find the optimum, but we try to have a power difference based on the predicted slope of 0.3 versus span loss, meaning that if you have a 3 dB power difference, for example, you should have a 1 dB 3 dB span loss difference. You should have a 1 dB power difference between the two spans. So that's what we are going to configure here in the spectrum information and the span information, sorry. The delta power range that we define is 2 dB in step of 2 dB. So we start with a very simple optimization with a raw granularity where you are going to launch higher power in the longer span, but for all other spans you are going to have the same power. So that can be a typical engineering choice in some for some vendors to only put higher power with higher power amplifiers in the longer span, but keep a very simple engineering with the same power in all other spans. So let's see the impact of that. And we run the simulation. And we are going to exploit the simulation result with the CSV file output, copying past the link, and put it there. So now you can see that my power sweep is finding that I can have a better SNR at the optimum launch power, and this launch power has been, this optimum launch power has been translated, because not all the power is the same in every span. And I still have something very simple in terms of configuration, because I have only a 2 dB power difference in some span, but I can see already an improvement in SNR. So that confirms, accordingly to the GN model, that launching a different power in every span is improving the performance. What happens if I want to push the exercise to what are doing some equipment vendor as well? A very high power differentiation in every span. So instead of having a 2 dB granularity, I now choose 0.5 dB granularity, and also allow to have a larger range of span range. So it means that the power difference between the span can reach 4 dB, and with 0.5 dB granularity. So basically the power is going to be different in every span. And let's see the impact of this engineering choice. So obviously it's a more complicated design. You have different power levels to manage. And again, we exploit our CSV result. And there you have it. So it's a very small improvement. It's maybe 0.1 or 0.2 dB, and obviously a lesser improvement than just having a rough span differentiation. But it's still some improvement. And the final engineering that we want to look at is the possibility to optimize the output VOA of the amplifier. So let's put it to true. So an output VOA is here to maximize the gain of the amplifier when there is some power and some gain margin. So that will basically improve the noise figure of all amplifiers in your network, especially on small span. And this can be automatically configured by the tool. But it has a cost. The amplifier has to support it. It basically needs to have an output VOA. So is it interesting to buy amplifiers with an output VOA that are more expensive? Let's look at it for this network. It's not general rules, of course, just an example. And plotting the result here. And you can see here we got some improvement, yes, because we have small span, so this is expected. And basically that's where we stop. I hope we could showcase some of the engineering customization that GNPy is offering. Thank you.